Okay, so hello everyone. As always, thanks again for joining us another day. Today is day 13 of the RH tutorial. And today, as we said in the previous tutorial, what we're going to do is to learn how to plot the response functions that we computed in the previous class. Okay, so, and I said learn to plot because it seems that it should be easy, but the truth is that when we did the SER online course, by default, SER uses a uniform optical depth step and also a uniform wavelength sampling. So we computed the response function analytically with the code, and then we just plotted the 2D, so the results. But in this case, if you remember, and I will mention it again later, we have used non-uniform grids for geometrical height. This was for saving computational time. And also wavelength dimension was not uniformly sampled because we also wanted to save time. And we knew that the core of the calcium line needed to be solved with a high spectral sampling, but the wings are not so, they don't change in short scales, so we had a coarse grid in the wings. So essentially, for saving time during the non-NLTE computation that is very expensive, we had these non-uniformly sampled grids. So then, okay, let's go just to the scripts and just check what we should do to properly read the results. So in this case, we will have, I prepared two scripts that are basically the same, one for the response functions that we computed to changes on the field strength, and a second one to the response functions that we computed when changing the temperature. Okay, so let's start with the the response function to changes in the field strength, and then we move to the other one. So the idea, as I said, we are going to see how we should plot the 2D response functions. And I think because I want to go slow in this case, I only focus on the 2D plots. But I think it would be nice if you can check as a homework to do some 1D plots where you pick some reference wavelength, for example, the line core wavelength of the calcium line, some wavelengths a bit farther from the line core, and then some wavelengths in the wing. And then you plot the response functions, for example, to the magnetic field or to the temperature versus height, and check how the line has a different peak depending on the wavelength. So for example, the core will have a peak in upper layers, and the wings, they have a peak in lower layers, indicating that the line is sensitive to a broad range of heights, but in different parts of the line. But this is always good, because if the same spectral region is sensitive to higher and lower layers, this could lead to uncertainties and degeneracies when determining the information of the atmosphere. Okay, so then if you have time, just give it a try at home for the 1D case. Okay, so today we start with the Stockz response function. Let me go to, so in the day 13 inside the Dropbox folder, there's multiple figures. So let me bring the one that we have from the SER course. So I will just put it here. 1 second. Okay, here. So the idea is that I wanted to start with this response function because I think it's very easy to see if things are reasonably okay or something went wrong. So the idea is that when we compute the Stockz V response function to changes on the magnetic field, and the magnetic field is reasonably simple, like in this case, is constant with height, you should expect a response function that it looks more or less like this. So it's like a Gaussian shape, where this is lower lower layers, is optical depth, so lower layers, and then it goes like this. And then you have that the line core, just the center of the line has almost no sensitivity or no sensitivity. And then you have that the response function has sensitivity beside that wavelength. And you have opposite sign between one side and the other side of the line center, the line core. So then the idea is that we are going to start evolving from the raw response function that we get from RH until we have something like this. Okay. So, and just as a note, this is important. So in this case, we are computing a response function that is from a constant magnetic field, very simple. So then in this case, you can expect that the Stockz V response function will be the one with highest signal, the most important one. But in general, we have 4 Stockz parameters, and when the magnetic field or the configuration of the atmosphere is more complex, this is not always the case. So you can have the Stockz I or Q and U, they can have mixed behavior. So just in this case, we can just focus on Stockz V and simplify the process. But in general, when you have a complex atmosphere, I think it's good to plot all the response functions for the 4 Stockz parameters, just in case the atmosphere is so complex that the sensitivity has changed from one parameter to the other. Okay, so then the first thing is we restore the save file that we computed in this rf.pro procedure from the previous class, and then just let's plot the response function. So in this case, what I'm going to plot is the Stockz V response function, and I just normalize it by the maximum of the response function, just for simplicity and for putting the bar from -1 to 1, like in this case. Okay, so then we go to this folder. So this is plot number 1. Okay, we have here number 1. So then let's see how this looks. Okay, so then you can already start seeing that the first thing is that is upside down, so we have to change that. But just to just note that this is the wavelength. This is now it's geometrical height because it's the atmosphere that we use, and I'm just picking this reference color bar. Okay, so then the first thing we need to do is very simple, but it's because you remember RH requires to start from the top of the atmosphere. So the first index of your array should be the top of the atmosphere, and then you go to lower layers as you increase the index on your array. So then I just defined a new geometrical height vector. I added this R that is from reverse, just because we are going to reverse. And then we need to define a new set of response functions that I also add the index reverse, and then we just run a loop. In this case, is on wavelength. So for each wavelength, we take the geometrical height or the height information and we reverse it. Okay, and this is for all wavelengths. So then when we do that, it's index 2, and this time we are plotting the Stockz V response function, the reverse one, normalized also by the reverse one, and we also keep the bar from -1 to 1. Okay, so then this number 2, it's simple. It's from the previous case, but just we reverse the axis. Okay, so then at this point you can say that this doesn't look like the one we have before, even if the one before was a LTE response function. So here things look a bit strange, and then, as I said, is because we have a non-uniform in both cases, in geometrical height and wavelength. So then we should start interpolating to a uniform grid, because at least this procedure, and I think in general, is not able to reproduce this non-uniform scale when you do the 2D plot. Okay, so then this is very simple to do. Okay, sorry. Just let me show you how the geometrical height is in this model. So have this plot
Carl,
here.
can I ask a question?
Yes.
I just didn't get what is strange in this figure 2,
Okay. So
which you just showed.
yes, the problem is so as I'm putting that the plot should go, let's go here. So I'm telling the y-axis should go from this value, that is the 0 value of the geometrical height, and goes up till the last value. So then the program is saying, okay, so the first value is like minus 400 or something like that. And the last value is 2200. So it's putting a uniform axis. Okay. But these values, they don't correspond to a uniform axis. So in fact, this value, I think, is around 1500 or something like that. So let me show you this plot.
Okay.
So the idea is that the plot and the axis is assuming that this is a straight line. But if you see it's linear in this case with one slope, then almost linear in this case with one slope, and then here is not linear at all. So then you are giving or assigning a height that it doesn't correspond to the real height of the response function, because the plot is assuming that each pixel corresponds to a uniformly sampled geometrical height.
Yeah, okay, I understand that now. Yeah.
Okay. Yes. So the main issue is that, so you can see that we have a lot of points here, and they just move from 2100 to 2200 or something like that. But the code is saying that here you have this small step. So let me do the interpolation, and you will see how this changed a lot. Okay. So then if we go back, we are going to do an interpolation. What I do is I just put this in kilometers, and then I'm going to pick a reasonably fine or very fine height step, and in this case is 1 kilometer, and I compute the number of points just using, so subtracting the top value minus the original one, so the origin, divided by the step, in this case is 1 kilometer, and then just adding this index. So with this, we have the number of points. So our new reverse geometrical height vector has that number of points multiplied by the sample and starting from the first point of the original geometrical height. And as we are going to interpolate the response functions, we need to define new arrays, where in this case, we are keeping the same wavelength domain, but now we have much more points in optical depth, sorry, in geometrical height. And then we again run the loop for each wavelength points, interpolating geometrical heights. Okay, so then now it's Stockz v reverse interpolated and normalized by the Stockz v response function, reverse and interpolated, and the index is 3. So Nancy, so just let me show you how it changed. So I will open the previous one and then the new one. So you can see that now it, 1 second. Oh, it doesn't fall. Sorry, it was not moving. So you can see that it's the same response function. We are just interpolated to a uniform grid and keeping the same height domain. So you can see that now we had a lot of points in this part of the response function that they were assumed to be in this range of height, but now it's properly represented or showing in the plot. Okay. Okay, so this is important, and I will emphasize it later again. So sometimes, and I talk from experience, when you use 2D arrays and they are not uniform sample, you can start making plots, analyzing the results, and then you realize that one of the issues is that it's not properly displayed by the procedure that you are using. So in this case, now we have a much better height behavior. But still, it looks like in wavelengths, it doesn't look very good. And we have a very nice wavelength sampling. So So then the problem here is again that is not uniform sample. So then let me go back to the ideal procedure, and I'm going to plot the wavelength vector. So just to explain you what is happening. So here, so this is how it looks. So if you remember, we had the broad wings of the line that they basically have almost no points. Then we have two photospheric lines in the left side of the so in shorter wavelength. So then we have uniform and dense spectral sampling between the two lines. Then we start in the calcium line, and we have a coarse sampling as we move far from the core, and then a very, very, very dense sampling in the line core. Then again, we move to the other side of the line, and the wavelength points, they become coarser. And then we have three photospheric lines. This is 1, 2, 3, and then the wings. So then you can see that if a code is assuming that this is uniform, it's really not making things correctly. So then let's try to interpolate to a wavelength grid that goes from this point to this point, but with a linear line. Okay. So then we do the same step as before. So in this case, I transform the wavelength vector to Armstrong because I used to work with Armstrong and milli-Armstrong, so I prefer to change it. But you can keep it in nanometers if you keep the rest of the things consistent. And in this case, I'm going to pick 10 milli-Armstrong step. That is, it's usually good for theoretical studies, but it's really good for observation. So if you pick 10, you can be in the safe side that this is really good for in the case of observations. Then the number of points is again the same. So I am picking the last wavelength point minus the first one divided by the wavelength step, that is 10 milliamps, and then just adding one index just to try to keep the same length. And then the new wavelength vector is the number of wavelength points that we had, an increasing vector with the weighted by the step that we want, that is 10 milliamps, and then starting at the initial wavelength point. And again, as we are going to interpolate, we also need to create a new set of response functions, that in this case is response functions, reverse, interpolated, because it's going to be the second interpolation, in this case in wavelength. So then we have the height points from the previous interpolation, and now we are changing the number of wavelength points, okay? So then also be aware that now the interpolation is in wavelength, so then our loop is going to run every height, okay? So for each height, we interpolate all the wavelength, and then next height, and then interpolate again, okay? So then when we finish that, we have index 4, and just again, this is the Stockz response function, reverse, interpolated in height, interpolated in wavelength, and then normalized by the same response function. Okay, so if we go to Stockz response function to B, and this is index 5, sorry, this is not, it's the index 4, this one, okay? So then we have not changed the response function in the sense that we haven't changed the amplitude or anything. We just interpolated to a uniform grid to make the plot better. So this is the same one we started from, and now you can see that it looks reasonable. So it's very smooth. It extends from around 0 to around 1,200, 500 kilometers. And then the spectral lines are narrow, and we have a very nice sampling. So you can see that this is smooth in the plot. Okay. So then just let me bring back everything that we have said. So in this plot, that is the one that I opened by mistake, I'm going to put 4 panels that we have covered. So first panel will be the regional response function normalized by that response function. Then the reverse one. Then the third panel will be interpolated. So the reverse and interpolated one in height. And the final one will be the reverse, interpolated in height, and interpolated in wavelength. Okay, So these are the steps that we have followed today. Okay, so again, the response function is the same, but the program that we are using for plotting is not really understanding that it's not uniformly sampled. So then the plots are not correct. At least in IDL, if you pick one wavelength and you plot it in 1D, and for example, the geometrical height is not uniform, there the behavior will be correct. So if you pick one, for example, one point here from the non-interpolated one and the interpolated one, and you overplot them, the results will be the same in 1D. The problem is when you have 2D. Okay, so just as a warning, always when you are displaying 2D arrays, just be sure that either your procedure can handle non-uniformly sampled arrays, or that you interpolate to a uniform sample array, and then you really are showing the behavior of the array that you want to show. Okay. So then the final thing, sorry, this looks okay, but maybe it's better to just make a zoom of this region, so just to see a bit better the response function. So then what we are going to do is we are going to make the zoom of that region, but I'm also going to bring the Stockz profile just to have a comparison between the response function and the Stockz profile. I think it would be nice to have it on top, but in this case, I prefer it to have it in 2 panels. So then I will show you later. But the first thing we need to do is to have the Stockz profile. And if you remember from the response function procedure, when we ended the program, we finished saving the response functions, but we didn't save any profile because this was a loop and it ran for multiple heights, and for each height we had a set of profiles. So then in that case, we didn't save it. My advice is you can just take the atmosphere and run the synthesis in one folder. I think this is probably the best thing, but as I think that's one easy way to do it. And what I did was I just went to the program. So remember that here we started, we started the loop, and then remember that we changed it, the parameter, in this case magnetic field, and we added the perturbation. We call RH, and then we save the results. So then I just added this stop, and I just saved these Stockz I, Q, U, and B, and this is what I'm going to use as a profile for the comparison. The idea is that it's not very stylish, but it's the first iteration of the loop. So it means that we are changing the magnetic field at 2,200 something kilometers. So there the response function, it's 0. So it means that the output of this synthesis should be the same as if you didn't change anything at all. So that for me is fine. But if it still is not fine with you and you don't want to create a new program, so just comment here this. So I mean, adding no perturbation, run the program, make a stop here, save the file, and then just put this back, and then you can have the profile. Okay. So you can decide how you do it, but the idea is that I just got the profiles from there, and let's use it for comparison. Okay. So then I restore the profile. I also interpolate it just to have it in the same wavelength grid as the response function. So everything is easier to plot, or if you want to overplot the results. So then is the original wavelength and the new wavelength, we interpolate, and then we make one last plot. Okay, this is index 6. Just let me briefly comment what I'm doing, and then we check the results. So we have 2 panels. In the second panel, I'm plotting the interpolated reverse response function, Stockz response function. In this case, in a shorter wavelength region, because we want to make a zoom of the region of interest, and then normalized by the response function in the same wavelength region. But then I'm adding a plot that is the new wavelength vector in this, again, the same number of points. And then Stockz and normalize by Stockz high in the continuum, okay? And then I also multiply by 100, so then the Y scale will be in percentage, okay? This is something that we usually do. So we normalize by the continuum intensity, and then Stockz Q, U, and V, we multiply them by 100. Okay, so then let's see how it looks. Let's make a zoom. Yeah, okay. So then it looks nice. So the profile is here, and we have the 2 lines that I mentioned in the left side, and then another 3 lines in the right side. And you can see that in general, where you have Stockz V signals, you also have the Stockz V response functions to the changes in the magnetic field. So in the continuum, you have white color, so there's no sensitivity to changes in the magnetic field there. And then you have that photospheric lines, they have larger Stockz V amplitude, and in this case also it seems that this having an impact on the response function, and the amplitude of the response function is also a bit larger. So I mean, the lines with larger amplitude, they seem in this case to show a higher intensity in the response function. And then we have the wings of calcium. You can see that I plotted horizontal line at 0. So you can see that the wing of the calcium 9 is very broad. And I would say that you see something here. And I guess this is what you see, this very weak shadow here. So it's because the wing is really, really broad. And then we get to the line core. And as we get to the line core, it moves to very, very high layers. So we go up to 1,500 kilometers in this model. And then you can see that it's very concentrated here, and there's no sensitivity here. And again, the wings, they move, they are broad. So I think, and yes, and I think there are some changes with height. I think there's some indication here of these changes of amplitude. And my impression is that this is related to the temperature gradient. So we have that the wings are forming more or less when the gradient of the temperature is going down, and then change, and then it starts to get hotter and hotter as you move to the chromosphere. So probably these changes that you see here are basically just that the temperature is being a bit complex there. Okay, so yes, so I think the main takeaway from here before going to the summary is that if you see this response function combined, so you have that these photospheric lines are like strong, they show sensitivity to changes in the magnetic field, and this amplitude means that even if the calcium line is not seen with high sensitivity in the photospheric field, those lines are seeing it. So you have like support for the photospheric magnetic field. And then the calcium line is very sensitive to higher layers in a broad range. So this window already is telling us that we can cover the magnetic field in a very broad range of heights from around 0 to 1,000, 1,200. Okay, so then let me see if I missed something. No, okay. So then before going to the summary and then moving to the temperature response function, is there any question until this point? No? Okay. Okay, so then just let me summarize what we did in this script, and then we will move to temperature. So then the idea is to save computational time, we run the synthesis, solving the radiative transfer equation in an atmosphere that was not uniformly sampled. So we had more points in the chromosphere because it's where NLTE is more important, and less point is in the photosphere. So we are saving time, but we are not losing accuracy. And the same for the wavelength range. So we have more points in the core where NLTE effects are important, and we have less spectral points in the wings where LTE usually can work very well. So again, we don't lose accuracy, but we save time. And so for properly or accurately representing the results in 2D, we need to interpolate both in geometrical height and in wavelength. And after doing this, the response functions, they look much better. And we saw that the calcium line is very sensitive to a broad range of heights. And if you combine it already with the photospheric lines in the wings, then you are increasing, I said height resolution, you can say it this way, or sensitivity also. So, but it's a good complement to have there. And then as a good comment is that the wavelength region that you saw with the spectral sampling that we use, it's going to be able to be observed with VISP on the keys. So we will have a spectrograph with polarimetry. We can have high spectral resolution. So this same window can be scanned with long slit instrument, a VISP. And this is very promising because, as I said, the line combined with the photospheric line in the windows, it seems to be very sensitive to a lot of heights. So then I'm looking forward to get the hands on this data. Okay, so now let's move to temperature. In this case, I prepared the script and I will give it to you. I basically changed the comments on the response function results, so I will not cover. What I'm going to cover is the plots, and while I'm showing different plots, I will just explain you some things. But the idea is that it's good if you can give it a quick look, because I just changed the information about how the response function look and other things. Okay, so but the figures are here inside the online course. So let's start with the first one. Again, the first thing that is strike us here is that it's upside down. So then we just reverse the rays. So we run the loop in wavelength and we change every height, and then we have it like this. Okay, but as I said, when you look something like this and you have been sure that you had a good spectral sampling and a good height sampling, then something is missing, and it's just that the program is not representing the reality. So then we interpolate in height. So now you can see that the line reaches higher, like 1400, something like that, but still the wavelength direction is not so good. So we interpolate in wavelength. Now it looks much better. Okay, so we have here thin lines, the photospheric lines. We have 3 here, then 2 here, and then the calcium line that is reaching high. And then before making the zoom in the region, just cover the 4 steps in the same plot. So we had it this way. We reverse the array, we interpolate in height, and then we interpolate in wavelength. So again, this response function is the same one that we have here, but the program is not properly representing it. So just be aware about that in the future when you receive an array from someone. Okay. Then let's do the same. So in this case, I'm just plotting Stockz I in a shorter wavelength region, and then I'm plotting below the Stockz I response function to temperature. So just be aware that all these plots, they were Stockz I response function to temperature. And in this case, I think in general, but I want to just warn, but I think in general, the Stockz parameter that is most sensitive to temperature is Stockz I. Okay, so then just as a quick plot, if you want to see the response of a given line to temperature, just plot the Stockz I. Although I think it's always good to have the 4 just in case. So then we have that in this case, it's not exactly like Stockz, the response functions to changes in the magnetic field, because there, besides, so outside the lines, we don't have signals. But here we have that the continuum is sensitive to changes in temperature, but at very low heights. And then you have that lines, they are like perturbations on these, in this case is the wing, but in general, in close to continuum, it will be like perturbations on this sensitivity. And they go up like a Gaussian in the case of LTE lines. And then we have 1, 2, 3, 4, and then you can see that the calcium goes up. And you can see that the correlation is clear. So you have the lines, so I mean the perturbation where the line is. But something that is interesting, and it really depends on the line, is that, for example, in this case, this one was the line producing larger amplitude in the Stockz V. But in this case, it seems that this line and probably this line, they look like they reach a bit higher in the atmosphere. So there's no exactly direct correlation on being a bit deeper and reaching higher in the atmosphere. This depends on the line and how the line forms and what type of mechanism contribute to the formation of the line. So just as an advice, if you have interesting lines and they look like very deep and things like that, it's always good to have accurate atomic parameters and give it a try to response functions, because there you can have a better information if the line being deeper means also reaching higher, or for any reason it means that it cannot be or cannot reach so high in the atmosphere. This can happen as well. Okay, and then this one, it looks almost buried in the plot, but the other two, even if they are almost the same, they reach much higher. So this is also interesting. And then you have that the calcium in this case, it's very nice because it's very smooth, and then you go to the line core. So calcium 28542, I think, is one of the best lines to cover temperature from the low photosphere to the middle chromosphere or lower chromosphere, because the line is very broad, but is sensitive to a very large range of height. So then, as before, I think this window is very promising, and being able to have it in single scan from one instrument with even high spatial resolution and high signal to noise is going to bring us a lot of new interesting things. So again, I think it's going to be very nice when WISP starts observing this region, because it's very promising. Okay, so I think with that, I probably covered everything. Yes. Okay, so then I will go back to the presentation. Is there any question before I continue? No? Okay, so then I added this section. So I think last week, Angel, he already also did the interpolation and plotted the response function. He used a different atmosphere, but he sent me the results, and I said, okay, let's plot it and in class and then show it to you. So then you can see that even very similar atmospheres, but just changing from geometrical height to optical depth or some elements will provide slightly different response function. But in this case, this is what he sent me. I think it looks more or less as what we had. So here again, it seems that this line is reaching a bit higher than this one. Even this one is deeper. Again, we have the same behavior. And then the Stockz V signals, sorry, the Stockz V response functions to the magnetic field, they are slightly different than what we had. I mentioned to him that I don't know, but probably it's because the scale is different and maybe the atmosphere is different. So if you remember, we had a larger amplitude here, almost comparable to the one in the line core of calcium. And in his case, it seems that the line core is much stronger than the photospheric lines. But I think these are just deviations from the nature of the atmosphere itself. But the general pattern seems to be the same. Okay, so just want to say thanks to Angel, because he sent it to me and I said, okay, I will put it in class. But I encourage you to do the same. So if you have time, try the atmosphere that you are interested on and check if things are reasonable after the interpolation. And if you want to share it with me also, that will be fine, because then I can have wider range of response functions to check and to examine. Okay. So then homework for you, as I said before, well, I always said the same. So just try to run the ideal script. If you use Python, just try to reproduce it with Python. And if you get some issue, just let me know. Just again, I repeated myself, but by experience, I just be sure that when you're plotting something, the program that you're using for plotting is really representing what you have in your array. And if not, just give it a thought or try to do an interpolation, something like that, because you can get different interpretations from the same thing, but just because there's an issue when you're plotting it or an interpretation of the program that you're using. So just be aware of that. And then, as I said in the beginning, I think it would be nice if you pick a few wavelengths in the line core, in the what they call the line knees. That is where it changes from the core to the proto wings, and maybe one wavelength in the wing, and just overplot them and check that the peaks of the response function, they go up and they go down with height, but this peak is shifting from lower layers when you are examining the wing to higher layers when you are examining the line core. Okay, so then next class, we go back. I think it's number 7. If I make a mistake, yes, I'm sorry. But it's just that we go to the class where we picked the bifrost atmosphere. We run the same program, changing units, convention, and everything. And then we save it with a format required for by the RH parallel wrap. And then we run the synthesis, and we run it over the same field of view that we use in day 8, and we will compare the results. So I will show you how to prepare the atmosphere, how to run the code, and then hopefully we will compare just one by one, or if not, just I will just let you do it. But it will be very easy to run the program, because there's not many options. So you will see that I can explain very quickly that. And that will be in December. We are reaching the end of the year, but I think we can have at least one class. I think if we add 2 weeks to December 10, will be December 24th. So maybe that day people will be busy, but at least December 10, we will have the next class. So then finally, is there any last question before I wish you a nice weekend and a nice week? No? Okay, so then enjoy the weekend. And as always, thanks a lot for being here today.
Bye, thank you.
Bye.
Bye.
Bye. See you.
Bye. Thank you, Carlos.
Bye.
Bye, thanks.
Bye.